Well, here we are, having discussed electric fields and electric potential energy, and we've defined the electric field as the force per charge. Namely, the electric field is electric force over charge. So that's basic definition. And we're now going to define another term, a related term. Very, very related, in fact. You'll actually notice that it's so related, it's just divided by a very simple quantity to equate the two. And even though I say that, it will perhaps be just a little bit mysterious nevertheless. So we're going to define electric potential. Yay! Now notice the energy part is not there. Electric potential. It's also just known as potential for short. And it's really easy to define. It's defined as the potential energy per charge. So here's a charge. It has some electric potential energy, as we've discussed. Divided by the charge itself, the quantity of charge, and you have the electric potential. So that's pretty easy, isn't it? Seems simple in principle. Well, the symbol, and how we write this, V for electric potential, is electric potential energy divided by charge, where electric potential energy corresponds to some position, like position A or B, because electric potential energy doesn't exist as an absolute quantity. When we talk about potential energy, it has to have a reference point. So we don't really directly measure V until we know from what the reference point is. So it's really a difference. So we can't measure it directly. There's other reasons for that too. We don't have a device just to measure it. But if we know what the electric potential energy is with respect to some other location, then we can figure out the difference between the electric potential energy and the reference point, which is what we mean for gravitational potential energy as well. When we talk about it, it's always like with respect to the floor or the ceiling or the surface of the planet or whatever. So we measure potential differences because the electric potential energy is with respect to positions. Well, the negative change in electric potential energy corresponds to the work done by the E field, as we discussed. So like in going from B to A, as, well, before. So the potential difference, V from B to A, that we have seen, is just meaning VB minus VA. VB minus VA, the difference in going from B to A. All right, including that negative sign, because change is final minus initial, right? So B to A, the change is A minus B. Negative of that, B minus A. So that's coming up again here. And that's work done by the electric field in moving the charge from B to A divided by the charge. So this is the equivalent of the electric potential energy. And it's joules per coulomb because that's the units. So VB minus VA is typically called voltage, and the unit is joules per coulomb, which is also volt, the symbol V. So there you have it. Now, as mentioned, this thing called potential, when we say like V sub A, V at A, the potential at A, it only makes sense if you have a reference. It only makes sense if the zero position is known, in other words. So in our example, here is maybe a VA. What's the potential at A? What's the potential at B? And it might be logical in this case to have as the reference the negative plate here. And so the potential at A with respect to, well, A, because that's where this charge is at the negative plate, would be 0. But at B, it's something else because it's with respect to A. Now, the 0 point for electric potential may be the Earth itself. It actually is in a lot of cases. The potential of Earth. And so when the physical charges are in the Earth, they have 0 potential. That's the idea. It's also called ground potential, The ground is the zero reference potential from which everything else is measured, with respect to which, in other words. Now for point charges, V is equal to 0 at infinity is sometimes a useful idea. Now I know I've just lost some of you. Don't worry. I may develop this a little bit more to your satisfaction, or perhaps not. But in any case, setting V is equal to 0 at infinity in some circumstances makes the mathematics easier, so that it reduces a term, and we're talking about potential differences. It simplifies things down to a single term. All right, so it's for convenience, but let's not worry about that too much at the moment. Now, as we think about potential, we have a change in potential energy of a charge Q as it moves through an electric field or an electric field force. For instance, from A to B, when we go from A to B, we're moving against that electric force. And the change in electric potential energy is UB minus UA, final minus initial, which, based on our definition now, is charge times the potential difference. Because, again, V is equal to energy divided by the charge. So that's the right form there, Q times VB. Right. Assuming that, potential at A is 0. So QVB minus QVA is what the whole thing is. But you don't even have to assume that the potential at A is 0. Whatever it is, QVB minus QVA is the change in electric potential. So that's QVBA, because the VBA corresponds to VB minus VA. So there it is, parsed out, so to speak. So that's greater than 0 in this case. As we already know, the electric potential energy is greater than 0. All right, I know this is all a little bit potentially confusing. And don't fret too much, but let me just summarize a little bit of what we said. So electric potential difference is a measure, really, of how much the energy of an electric charge is changed, or how much you can acquire in a given situation. So if the positive charge goes toward the positive plate, like it is here, it gains potential energy. That's pretty obvious. It's the same thing as saying that when a positive charge goes against the E field, see, there's an E field from here to here. When the positive charge goes against it, there is a rise in potential energy. The potential energy rises. If the charge gains potential energy, the potential of the charge rises. Now, this is all with respect to a positive charge. Because if this was a negative charge, it would go zoop. It would, going from A to B, it would lose potential energy. And so that's the one additional nuance that has to just be kept in mind. That if we reverse, this is all based on positive test charges. If they're negative charges, then the potential energy consideration reverses. But it is true that any time, regardless of whether there's charges there or not, if we go against an electric field, which would be going in this direction, that we rise in potential, we gain potential. And we're going to relate that to gravitational potential, which will just help bring this home a little bit.